Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is AC current sources. Our objective is to introduce AC current sources and perform circuit analysis using AC current sources. Additionally, we'll discuss rules and regulations regarding AC current sources and the limitations of real-world AC current sources. An AC current source is a supply element that will push current of a given preset value through a circuit despite changes in impedance. In theory, an AC current source could push 2 amps at an angle of 0 through a 20 ohm impedance as easily as it could a 20 mega ohm impedance, but the real world says differently. We'll discuss limitations of real-world AC current sources in a moment, but for now, we'll just assume AC current sources behave exactly like they're supposed to. Regardless of the applied load impedance, an AC current source pushes the required amount of sinusoidal current through it. Given sinusoidal AC current continually changes not only in magnitude, but also polarity, the arrow in the schematic symbol is of dubious utility when considered in isolation. However, polarity is important when a circuit includes more than one source. The arrow simply implies that at the start of the analysis, current happens to be traveling in the direction of the arrow. The same thing can be said about the polarity markers for an AC voltage source. They're kind of purposeless when considered in isolation. However, they're super important when a circuit includes more than one source. Polarity markers simply imply that at the start of the analysis, polarity initiates the cycle as indicated. You'll be happy to know if we keep AC current sources at the simple level of mathematical abstraction, circuit analysis using AC current sources is exceptionally easy. With 2 amps at an angle of 0, traveling through an impedance of 20 ohms at an angle of 0, an application of Ohm's law shows us the voltage drop across it will be 40 volts at an angle of 0 degrees. An application of the AC power formula demonstrates the AC current source is delivering 80 volt amperes of apparent power, of which 80 watts is directed towards real power and 0 VARs towards the reactive interchange. When we swap out this initial load for one with an impedance of 20 mega ohms at an angle of 0 degrees, another application of Ohm's law shows us that the voltage drop across it will be 40 megavolts at an angle of 0 degrees. An application of the AC power formula demonstrates the AC current source is delivering 80 megavolt amperes of apparent power, of which 80 megawatts is directed towards real power and 0 VARs towards a reactive interchange. 80 megawatts. Can you see the difficulty in purchasing a real-world current source that can push 2 amps through a circuit regardless of applied load? It's not gonna happen. However, if we're willing to suspend our belief in physics, sure, it could happen, and our Ohm's law analysis gives us the necessary proof it could. The AC current divider rule is an especially handy technique when performing circuit analysis using AC current sources. For reasons I'll explain in later lectures, AC current sources are often placed in parallel with a fixed impedance and a variable load impedance. This parallel relationship is a perfect setup for the AC current divider rule. Incoming current is known, as are the impedance values. Consider an AC current source supplying 50 milliamperes at an angle of 0 degrees to a parallel combination of impedances. One, a fixed impedance of 480 ohms at an angle of 30 degrees, another, a variable impedance currently set at 240 ohms at an angle of 0 degrees. An application of the AC current divider rule demonstrates that current through the variable load impedance is 34.4 milliamperes at an angle of 9.9 degrees. Having calculated 34.4 milliamperes at an angle of 9.9 degrees of the incoming 50 milliamperes at an angle of 0 degrees is traveling through the variable load impedance, and applications of Kirchoff's current law demonstrates that the remaining 17.2 milliamperes at an angle of negative 20.1 degrees of current is traveling through the fixed impedance. Current with a larger magnitude is traveling through the smaller magnitude variable load impedance. Conversely, current with a smaller magnitude is traveling through our larger magnitude fixed impedance. It makes sense. Accounting for phase shift, the summation of both outgoing current paths equals the incoming current. We can be reasonably certain our results are correct. An application of Ohm's law demonstrates the voltage across the variable load impedance to be 8.2 volts at an angle of 9.9 degrees. Since the fixed impedance is in parallel with our variable load impedance, it can be said, no calculations needed, that voltage across the fixed load impedance to be also 8.2 volts at an angle of 9.9 degrees. Voltage across elements in parallel is the same. This is the most fundamental property of parallel circuits. Similarly, an application of Kirchoff's voltage law demonstrates that this drop must be caused by an equal and opposite voltage rise of 8.2 volts at an angle of 9.9 degrees produced by the current source. This is the voltage magnitude and phase shift necessary to push 50 milliamperes at an angle of 0 degrees through this parallel impedance combination. Let's say we reduce our variable load impedance and shift its angle to 150 ohms at an angle of negative 20 degrees. By all means, pause the lecture and see if you can solve for current through the variable load impedance and the voltage across it on your own. If you're tracking, you should have obtained the following results. An application of the AC current divider rule demonstrates that current through the variable load impedance set at 150 ohms at an angle of negative 20 degrees is approximately 40.8 milliamperes at an angle of 11.3 degrees. Having calculated 40.8 milliamperes at an angle of 11.3 degrees of the incoming 50 milliamperes at an angle of 0 degrees is traveling through the variable load impedance, an application of Kirchoff's current law demonstrates that the remaining 12.8 milliamperes at an angle of negative 38.7 degrees of current is traveling through the fixed impedance. An application of Ohm's law demonstrates the voltage across the parallel combination of the variable load impedance and the fixed impedance to be 6.1 volts at an angle of negative 8.7 degrees. This voltage drop must be caused by an equal and opposite voltage rise of 6.1 volts at an angle of negative 8.7 degrees produced by the current source. This is the voltage magnitude and phase shift necessary to push 50 milliamperes at an angle of 0 degrees through this particular impedance pairing. Note the magnitude is less than our previous implementation. It makes sense. With our variable impedance presenting less opposition to current, the voltage needn't be as high to keep current at the desired 50 milliampere set point. Keep in mind that AC current sources aren't exclusively limited to pure parallel circuits. They could also be included in basic series circuits or more advanced series parallel circuits. Consider a 40 milliampere AC current source in this series circuit consisting of Z1, a non-ideal inductor that happens to present a complex impedance of 172 ohms at an angle of 83 degrees at the given excitation frequency, Z2, a resistor that happens to present a complex impedance of 240 ohms at an angle of 0 degrees, and Z3, a capacitor that happens to present a complex impedance of 57 ohms at an angle of negative 90 degrees at the given excitation frequency. The most fundamental property of series circuits is that current through elements in a series relationship is the same. The current source, being the only active source in our circuit, must therefore push 40 milliamperes of current at an angle of 0 degrees through the whole circuit. Source current equals current through element 1, which equals current through element 2, which equals current through element 3. By all means, pause the lecture and see if you can solve for the voltage drop across each impedance. If you're tracking, you should have obtained the following results.